Imagine stepping into a tunnel and emerging centuries into the future, or traveling back to witness the birth of the pyramids. For decades, science fiction has fueled our fascination with time travel, but could wormholes, the mysterious cosmic shortcuts predicted by Einstein, actually make it real? In today's video, we're diving deep into one of the most mind-bending questions in physics. Is time travel through wormholes actually possible? Stay with us as we explore the tantalizing theories, the staggering challenges, and whether humanity might one day navigate the corridors of space-time itself. Wormholes, also called Einstein-Rosen bridges, are hypothetical passages through space-time, potentially linking distant parts of the universe or even different times. Imagine bending a piece of paper so that two points touch, then piercing a hole through them. Instead of traveling across the paper's surface, you jump directly between the 2 points. That's essentially what a wormhole could be, a cosmic shortcut. While these solutions exist mathematically in Einstein's equations of general relativity, we've never observed a real wormhole. The concept is incredibly alluring because it suggests not only faster than light travel, but also the possibility of time travel itself. But is that just theoretical fantasy or something achievable? Here's where things get wild. Some physicists propose that if you manipulate one mouth of a wormhole, say by accelerating it close to light speed, it experiences time differently due to time dilation, a proven effect in special relativity. When you bring the wormhole mouths back together, you'd effectively create a time difference between the two ends. Traveling through the wormhole would mean stepping into a time machine, emerging in the past or future relative to where you started. The math supports it under very specific conditions. However, the energy requirements and physical stability pose daunting obstacles. Still, the idea fascinates scientists and sci-fi fans alike because it doesn't outright break the laws of physics, just stretches them to their limits. A critical problem with wormholes is keeping them open. Left on their own, wormholes would instantly collapse due to the immense gravitational forces trying to close them. Physicists believe that exotic matter with negative energy density might hold a wormhole open. This exotic matter would exert outward pressure to counteract gravity. Quantum effects, like the Casimir effect, hint that negative energy does exist, at least in tiny amounts. However, creating enough exotic matter to stabilize a wormhole big enough for a human, or even a subatomic particle to travel through, is beyond anything our technology can currently achieve. Without it, a wormhole remains a cosmic curiosity rather than a practical time machine. Even if we built a stable wormhole, time travel raises enormous paradoxes. What happens if you travel back and prevent your own birth? A classic grandfather paradox. Physicists have wrestled with these questions for decades. Some suggest that the universe might enforce self-consistency. Events unfold in a way that prevents paradoxes, no matter what. Others propose the many worlds interpretation, where traveling through a wormhole might deposit you into a parallel universe instead of changing your own past. Stephen Hawking introduced the chronology protection conjecture, proposing that the laws of physics prevent time travel altogether to preserve causality. The debate remains open, reflecting just how profound the implications of time travel through wormholes would be. So, is time travel through wormholes actually possible? The honest answer, theoretically, yes, but practically, we're nowhere near making it happen. Our understanding of physics allows for wormholes and even suggests they could connect different times. Yet the obstacles are immense. Exotic matter, cosmic stability, and paradoxes all stand in our way. No evidence suggests wormholes exist in the real universe, and the energies involved are far beyond what humanity can currently produce. Still, research continues because exploring these ideas pushes the boundaries of human knowledge. Who knows? Someday, a breakthrough in quantum gravity or exotic physics might turn science fiction into science fact. Einstein's theory of general relativity gave us the mathematical foundation for wormholes. In the 1930s, Einstein and physicist Nathan Rosen introduced the concept of bridges in spacetime, what we now call Einstein-Rosen bridges. These were purely theoretical constructs, solutions to the equations of gravity. But even then, they realized that these wormholes would be unstable. While they never envisioned practical time machines, their equations ignited generations of curiosity. Today, physicists are still building on Einstein's work, trying to balance the space-time geometry required to create a stable wormhole. But the equations are unforgiving. Any small fluctuation collapses the structure. Einstein opened the door, but we still don't know how to walk through it. Physicist Kip Thorne brought wormholes into the public spotlight when he advised on the film Interstellar. Thorne took the concept seriously and even wrote a paper on how a wormhole could, in theory, be traversable. His work required manipulating exotic matter and precise conditions, but it stayed within the boundaries of known physics. The rotating black hole portrayed in the film was based on real calculations. While Thorne acknowledged the practical impossibility for now, his work legitimized the discussion around wormholes and time travel in scientific circles. He proved that the ideas weren't just science fiction, they were grounded in scientific plausibility. Some physicists believe there's a deep link between wormholes and quantum entanglement. A revolutionary idea proposed by Leonard Susskind and Juan Maldacena is the ER equals EPR conjecture. It suggests that wormholes, Einstein-Rosen bridges, and entangled particles, Einstein-Podolsky-Rosen pairs, are two sides of the same coin. This implies that space-time itself might be stitched together through quantum entanglement. If true, this opens the door to microscopic wormholes and possibly even new ways of encoding or transmitting information through time. It's a bold and still speculative theory, but one that could tie the mysteries of quantum physics to the curvature of space-time. Black holes have always fascinated scientists for their strange behavior. Some theories propose that deep inside a black hole, there could be a wormhole, a tunnel leading elsewhere in the universe or to another time. The problem is, crossing the event horizon seems to trap anything forever. Yet, in theory, a rotating or charged black hole might contain a passage to a white hole, the other end of a wormhole that expels matter instead of absorbing it. However, white holes are hypothetical and have never been observed. Still, this speculation keeps the dream alive that perhaps black holes could be more than just cosmic destroyers, they could be doors. One of the greatest hurdles in wormhole time travel is the cosmic speed limit, the speed of light. According to Einstein, nothing with mass can move faster than light. But wormholes, in theory, cheat that rule by curving space itself. You're not moving faster, you're taking a shortcut. This concept redefines how we think about distance and time. If two wormhole mouths are far apart, you could instantly leap between them. Yet, ensuring both mouths stay synchronized across time and space is where the paradoxes creep in. While wormholes don't break the light speed rule directly, they challenge how we perceive space-time travel. Stephen Hawking, perhaps the most recognized physicist of our time, was skeptical of time travel. He proposed the chronology protection conjecture, a principle suggesting that the laws of physics prevent time travel to preserve causality. Hawking pointed out that even if wormholes allowed time travel, radiation and quantum fluctuations would destroy the time machine before any paradox could occur. This conjecture, while unproven, remains a serious consideration. According to Hawking, nature has a way of protecting itself from logical contradictions, making true time travel an elegant impossibility rather than a future reality. To stabilize a wormhole, scientists speculate we need negative energy or negative mass. These exotic concepts are nothing like ordinary matter. Negative energy would exert a repulsive gravitational effect, exactly what's needed to keep a wormhole open. Quantum mechanics has shown that negative energy is possible on tiny scales. The Casimir effect, for example, creates a measurable force using vacuum fluctuations. But harvesting and amplifying such energy on macroscopic levels is far beyond our capabilities. Until we can understand and manipulate negative energy in a controlled way, the dream of stable wormholes remains a long shot. In 1988, physicists Morris and Thorne introduced the idea of traversable wormholes, structures that could be crossed without collapsing. They laid out the conditions such a wormhole must satisfy, including being held open by exotic matter. These theoretical blueprints energized research in both relativity and quantum fields. However, creating one would require manipulating space-time itself with immense precision and unknown technology. We would need control over gravity on a scale currently unimaginable. While it's mathematically feasible, no known process in the universe naturally creates such wormholes. It's a perfect case of theory outpacing reality, at least for now. Some scientists wonder, what if wormholes already exist, hidden in the fabric of space? They could be microscopic, woven into the quantum foam at the Planck scale, far smaller than atoms. These wormholes might constantly form and collapse due to quantum fluctuations. While they'd be too small to travel through, their existence could hint at a deeper layer of reality. Some even propose that dark matter or dark energy effects might be caused by hidden wormhole structures. It's speculative, yes, but it opens fascinating possibilities for future detection through gravitational waves or high-energy cosmic observations. String theory, one of the leading candidates for a theory of everything, suggests that all particles are tiny vibrating strings in higher dimensional space. In some versions of string theory, wormholes arise naturally as geometric solutions. These extra dimensions might allow for stable wormholes or even time loops. However, string theory is incredibly complex and not yet testable. But if proven true, it could provide the framework for understanding how wormholes operate and how they could be manipulated. It may even offer clues to building or discovering natural wormhole pathways in our universe. Some thinkers propose that if we live in a simulation, wormholes and time travel might not be governed by physics as we know them. In a simulated universe, what we see as the laws of physics could be adjustable parameters. Time portals might just be software loops or shortcuts in the code. While this is philosophical and not scientific in the traditional sense, it's an idea that adds another layer to our understanding. If time is a variable, not a constant, and reality itself is programmable, then wormholes could be engineered rather than discovered. Stories have emerged, though unconfirmed, of government projects investigating wormholes and time travel. The U.S. Defense Intelligence Agency, DIA, for instance, once funded research into warp drives and traversable wormholes as part of the infamous Advanced Aerospace Threat Identification Program, ATIP. While the results were theoretical, the very fact that such work received funding shows that these ideas are taken seriously at some levels. Could secret labs be trying to crack the space-time code? Possibly. But if so, we've seen no public success, yet. If intelligent alien civilizations exist and are more advanced than we are, it's not unreasonable to speculate that they could have mastered wormhole travel. Some scientists have even suggested that unexplained phenomena, such as fast radio bursts or UFO sightings, might be tied to wormhole entrances or exotic propulsion. If wormholes can be stabilized and used, a civilization could instantly cross galactic distances. That might explain why we haven't detected clear signals. They're not sending messages, they're traveling. It's still pure speculation, but wormholes remain a favorite in the toolkit of theories for advanced extraterrestrial travel. From Doctor Who and Stargate to Rick and Morty, wormholes have been a favorite device in pop culture. These stories make the impossible feel plausible and often inspire real scientific questions. While Hollywood dramatizes wormholes with glowing portals and instant jumps, the real science is far more complex. Still, fiction has a role. It helps visualize abstract concepts and inspires young scientists to dig deeper. Sometimes, today's fiction becomes tomorrow's fact. Just look at submarines, rockets, and even the internet. Once science fiction, now reality. We may be centuries from opening a wormhole, or we may find one hiding in the cosmos tomorrow. What's clear is that our fascination with time travel is deeply human. We long to rewrite the past, predict the future, and escape the linear flow of time. Whether wormholes will become cosmic highways or remain untestable math depends on future breakthroughs in physics, energy, and our understanding of the universe's deepest laws. Until then, The concept of wormhole time travel remains a beacon of curiosity, a question that challenges us to imagine the unimaginable. Even if we discovered how to create or stabilize a wormhole, the energy cost would be astronomical. Some estimates suggest you'd need the mass energy equivalent of an entire star to hold open a human-sized wormhole. We're talking energy levels far beyond anything humanity has ever harnessed. To put it in perspective, the entire output of the sun for thousands of years might be required. This colossal energy barrier makes wormholes an engineering impossibility for now. Until we discover new physics, the cost of wormhole construction remains firmly out of reach. An intriguing question arises. If time travel through wormholes is possible, where are the time travelers? Some scientists argue that their absence suggests time travel isn't feasible. Others counter that time travelers might hide to avoid altering history or being detected. Or perhaps wormholes can only connect to the future from the moment they're created, preventing journeys into our past. While the idea fuels countless conspiracy theories, there's zero evidence that travelers from the future walk among us. But it's a question that keeps both scientists and sci-fi fans awake at night. One terrifying aspect of time travel is the butterfly effect. The notion that small changes in the past can create massive, unpredictable consequences in the future. Even walking through a wormhole into the past might inadvertently shift history in ways we can't foresee. Kill a mosquito in ancient Egypt, and you might return to a future where humans never evolved. Physicists debate whether the universe allows such freedom, or whether time is self-consistent and prevents paradoxes. Wormhole time travel makes this debate even sharper, since stepping through one might literally change history. Fermi's paradox asks, if intelligent aliens exist, why don't we see them? One bold idea is that advanced civilizations might use wormholes to explore or migrate without revealing their presence. Instead of sending slow radio signals, they might travel instantly through space-time. If so, they could remain invisible to our telescopes, popping in and out of distant places without leaving evidence. While speculative, wormholes might offer a solution to why the galaxy seems so quiet despite billions of stars. Despite the obstacles, scientists continue to explore wormholes, motivated by both curiosity and practical questions. Research into quantum gravity, string theory, and space-time geometry may unlock secrets that make wormholes more than just theoretical constructs. Institutions worldwide, including NASA and major universities, have published papers exploring exotic spacetime solutions. Even if practical wormholes remain centuries away, studying them teaches us profound truths about the universe. Wormholes sit at the crossroads of relativity, quantum physics, and cosmic possibility. The multiverse theory suggests countless parallel universes might exist, each with its own laws of physics. Some scientists propose that wormholes could connect these universes, allowing travel not only through space and time, but into entirely new realities. Entering a wormhole might deposit you in a universe where Earth never formed, or where dinosaurs still rule. It's a concept that stretches imagination to the breaking point, but it's consistent with some modern theories. If wormholes exist, they might not merely link places and times, but countless versions of existence itself. Some fringe theories propose that consciousness itself might traverse wormholes, independent of physical bodies. This idea merges physics with metaphysics, suggesting the mind could exist as pure information, traveling through cosmic shortcuts. While there's no evidence to support this, the concept fascinates philosophers and scientists alike. Could wormholes one day be the highways not only for matter, but for thought and identity? It's a radical idea, but it shows how wormholes push us to reimagine reality itself. Artificial intelligence is becoming crucial in exploring complex physics problems. AI algorithms can analyze vast mathematical models and simulate conditions we can't replicate in labs. Researchers are using AI to study exotic spacetime geometries and search for viable wormhole solutions. While AI won't build a wormhole anytime soon, it might uncover theoretical insights faster than humans alone. If wormholes exist, AI might be the key to finding them, or proving they're impossible. In 2015, scientists detected gravitational waves for the first time, ripples in space-time from colliding black holes. Some researchers now speculate that wormholes could produce unique gravitational wave signatures distinguishable from those of black holes. If future detectors become sensitive enough, we might discover wormholes indirectly through their gravitational echoes. This method offers one of the most promising ways to test whether wormholes exist in our universe. It's a thrilling prospect, a cosmic fingerprint waiting to be discovered. Quantum tunneling allows particles to cross energy barriers they shouldn't be able to overcome. Some physicists wonder if quantum tunneling could create tiny, fleeting wormholes at subatomic scales. These wormholes would be far too small for people, or even particles, to travel through, but they could reveal how space-time behaves at quantum levels. Studying these fleeting phenomena might help unify gravity and quantum mechanics, solving one of physics' greatest puzzles. Black holes famously create an information paradox, the question of whether information falling into a black hole is lost forever.